Hello everyone, my name is Borja and I'm going to be presenting this work about systematic organization in deep reinforcement learning that I've done with the amazing collaboration of Mark Sanahan and Francesco Lardinelli. So one of the main struggles of deep reinforcement learning agents that follow human-given instructions or of reinforcement learning agents in general is auto-distribution generalization. What is that? Well, imagine that I have trained my robot or my agent to do some task, and then I ask my agent to do the same task, but apply to a new object. The agent will struggle to do that. And the same will happen if I ask my agent to do the training task, but in a novel environment. So this, of course, makes the auto-distribution generalization a very active line of research. And recently, a popular approach is to work with temporal logic to express instructions for reinforcement learning agents. Why temporal logic? Well, because it offers unambiguous semantics, compact and compositional syntax that is easy to use by symbolic models to do some forms of generalization that we will later see. And it's naturally fitted for procedurally generated environments. So the unambiguous semantics let us procedurally generate a reward function. And with what I say after about procedurally generated environments, it's very important because when we're targeting generalization with reinforcement learning agents, we cannot just use fixed environments. The agents will learn just to memorize them. So the state of the art of temporal logic with reinforcement learning has some key insights that are, first, we have a set of neural submodels that are just reinforcement learning algorithm. Each of them specialize in a subtask. For instance, a subtask could be bring me the phone. Then we have a symbolic module that handles the complex formulas. Like, for instance, if we ask turn on the lights and then bring me the phone, the symbolic module says, okay, we first have to turn on the lights and then bring the phone. So first we activate the reinforcement learning agent that has learned to turn on the lights, and then the one that has learned to do the second subtask. What is the main drawback of this approach? Well, that we need a new neural model to do each subtask. And by each subtask, I mean that if we ask the agent to do the task, bring me the pen, we will need a different reinforcement learning agent that has been trained from scratch, and we cannot reuse information from bring me the phone or any other related task. So as we increase the number of tasks that we have to do, we have to train more and more agents, and this becomes more and more unfeasible. So as we hope it's obvious, we want to change that, and we want to bring act as a bridge between the learning generalization literature and the symbolic generalization literature. So we propose to keep this symbolic module and neural module dichotomy, as in the previous literature I was mentioning. But for instance, one change that we propose to do is to change the symbolic module so that we remove redundant operators, like eventually is very common. But if we ask our agent to do some task, we are already implying that we want this to be done eventually, not right now in this very second. So another change that is more important is that we change the order of the negation operator. We saw that if instead of saying not some atom, same some atom, and then not, so pen not pen instead of pen not, we see that this helps with visually given instructions when the agent is learning to unite systematically those instructions. But the most important feature, the novel feature of our work, is a neural model that is capable of systematic generalization. This is not trivial for learning agents. But before diving into it, I'm going to give a quick example of what is systematic or compositional generalization. This is something that humans are very good at, and as an example, if I ask you, do you know how to DAX? You probably will say no, because I just made up this word. But if I tell you that this is how you DAX, now if I ask you, could you DAX twice or DAX like you mean it, you will probably know how to do it, because you know from the picture what is this task about, and since you have learned how to do this task, you can combine it with your previous knowledge of different instructions or contexts where you have to do something twice or do something like you mean it. We want our agents to do a similar thing. And specifically in the experiments that we're going to be doing, we want to see that if our agents know how to perform an action and the agent knows what is the object that I'm referring to, so for instance, if I say the phone, the agent knows what the word phone refers to, the agent should be able to do that task, get the phone, even though that I never explicitly train the agent to do this specific task, okay? So in our context that is of systematization, we're working with abstract operators because, as I was explaining before, we're working with temporal logic. We want abstract operators like negation or disjunction, the agent to learn them systematically. But there's very little research in deep reinforcement learning agents that can do this. And the most important and most recent literature on this topic, previous to ours, is the one from Heath et al. And colleagues that focus on negation and say that that while with positive instructions, agents can learn systematically from as little as 6 different instructions. For abstract operators such as negation, 100 different instructions are a must. Nevertheless, we prove that this can be overcome, and we can have the reinforcement learning agents that generalize from 6 instructions with abstract operators as well. But we found a key missing feature that wasn't mentioned in that previous research, or wasn't found in that previous research. So, and it is that the way that agents see their environment affects greatly their learning strategy. By that we mean that the convolutional layers that we use, so the CNN architecture that we use, are going to have a key role in the emergence of systematic learning in our agent. And contrary to previous research that was stating that we are required to have, it's just better to have deeper and deeper networks, was always putting the focus on using residual nets, we found that actually it's not so much about residuals or convolutional networks, but about the kernel size, the stride size, and the visual embedding generated by the convolution layers. But the visual embedding, we're just referring to the output of the convolution layers of the architecture. So, for instance, if we're working with a grid wall environment, we found different behaviors and according to how specialized was the convolutional architecture to this environment. So in the grid wall, we say that an architecture is weakly aligned if the kernel and stride size are factors of the tile resolution of the environment. If besides of these two features, we have that the visual embeddings are representing each of the tiles as a 1-by-1 feature with n channels, with n being a natural number, we say the architecture is strongly aligned. And if none of this happens, we say that it's not aligned. Intuitively, what we're saying is that depending on how easy it is to infer from the visual embedding that there are independent objects and that the independent objects that are in the environment, the easier it's going to be for the agent to learn to generalize systematically. So in our work, we have we test with 2 benchmarks. One is the Minecraft Spire environment that is very popular in temporal logic with reinforcement learning literature, and the other is the mini-grid environment that is very popular in the reinforcement learning generalization in reinforcement learning literature. The key difference between the two are that tile resolutions are different between these two, and more importantly, that the instructions are visually given in the Minecraft Spire environment, while in mini-grid instructions are given as text. In here, what we ask the agent is to navigate towards certain objects or objects, and this can be done by a positive instruction, just saying the object, or saying the object that we don't want, like saying we don't reach the gray ball node, as an example you see, and we're asking for any object that is different from a gray ball, or with a disjunction, as you see on the example on the left. So the agents are given a small penalization at each time step to encourage them to solve the specification. Large penalization if they are getting an object that is not the one we want, positive and a positive reward if they are getting the object that is set in that satisfies the instruction. So for each of the environments, we use we explore with different convolutional neural networks and residual networks that are of each kind that we expressed before, and that we also work with a strongly aligned architecture that has random features. By random features, we mean that we just initialize the network and we froze the convolution layers before training, and we kept the weights that way forever. Note that we also do a train validation test split. This is not common in reinforcement learning literature, but as you are going to see now, some of the agents just learn to overfit to the training instructions, and in an attempt to stop that from happening, what we did was this train validation test split to do some early stopping, but still, as you're going to see, that's not going to stop some agents from overfitting, and the results that you're going to see are the ones obtained by the weights that achieve the best performance in the validation set. So if we look at only at the raw performance of the agents, wouldn't be enough to tell if they are learning compositionally or not. So what we do is having binary choice maps where we have some reliable instructions. So when we're having reliable instructions, the instructions point to objects that grant a positive reward for the agent, while we have then other tests where we have deceptive instructions, where the instruction points to an object that is going to grant a penalization to the agent. Since the agents were always learning to follow instructions, in these zero-shot experiments, there should be a very large difference between the reliable and deceptive results if the agents are already learning to follow instructions. And the things that we notice is that the not aligned architectures are in many cases not caring at all about the instructions because they are having the same performance between the reliable and deceptive setting. And if you see, it's not that the residual net is better than the Atari, because in this case the residual net is not on an architecture but in the mini grid where instructions are given as text. We check the weak aligned results. We see that the residual net is not doing that well when it's weakly aligned in Minecraft environment, and in mini grid where, as I said, it is not as dependent on the convolution for the instructions as in Minecraft. We see that the weakly aligned architecture is almost able to generalize well with all the operators. We see then that only the strongly aligned architecture is able to show a strong difference between reliable and deceptive settings in all the environments with all the operators. And more importantly, we see that just with the right architecture with random features, we achieve better systematization than the non-aligned architectures. And note that here we're comparing a residual net with a swallow convolutional neural network. So the results that we have for the symbolic model with the neural model are with the same kind of experiments, but now we are using longer instructions, all of them zero-shot, as it's ones you see here. So the symbolic model is just decomposing the instructions of tasks that can be done, in this case, by just one neural model that was trained just to do this task independently, but just one reinforcement learning algorithm, just one neural network. And as you can see in the table below, of course, the ones that are learning to generalize, so the strongly aligned networks are the ones that are achieving better rewards, even though that might be taking more steps, because the others would have learned is just to navigate quickly towards the objects. So the takeaways of our research are that symbolic initialization and learning-based initialization, as we are reading here, is a promising path for reinforcement learning. The deep reinforcement learning agents can learn abstract operators in a systematic fashion from as little as 6 examples, so from as soon as with positive instructions, and that the convolutional neural networks, the convolutional layers play a key role. Of course, in visually continuous environments, it's very important that we use methods that automatically can find the right architecture, because what we use, that handcrafted architecture, can only be applied to grid walls. But as we mentioned before, what we found is that we need to have independent representations of the objects from the visual embedding, and then the agents will be able to generalize well. So thank you for listening. We hope to see you in the Q&A session and in the poster, and here you can find the paper and the code. Thank you.